My name is Daniel Freund, and together with Harry Ong and Davide Krappi, I'll be presenting our work on Lyft's innovations in driver positioning and incentive budgeting. Before I start, I want to thank the prize committee for their diligent work so far and for giving us the opportunity to present here today. It's quite humbling for us to have been selected as a finalist alongside such inspiring other projects that really exemplify Inform's motto, analytics for a better world. With that said, let me get started. The work we present has close connections to dynamic pricing in ride-hailing. For context, ride-hailing platforms like Lyft employ dynamic pricing as a mechanism to match supply and demand. When demand for rides is higher than what the supply of drivers can serve, the platform increases the price for riders to deter them from requesting. At Lyft, we call this dynamic pricing prime time, and it's abbreviated as PT. By deterring some riders through prime time, the platform ensures that the number of drivers that remain idle is sufficient for platform service levels to remain high. This relates in particular to pickup times, which we want to remain low for drivers that are not deterred by prime time, that are still requesting despite the higher prices. Such low pickup times are of importance for both drivers and riders. Drivers need low pickup times because it increases their utilization, and riders want to avoid long waits for service. However, so far, or traditionally at least, the dynamic pricing experience has really only focused on the rider side. For the drivers, the legacy experience was really just a display of the instantaneous rider output prices. You see it in the figure on the slide. The drivers just observed the location at which riders were currently presented with higher prices. This driver experience had several shortcomings. Specifically, it made it really difficult and complicated for drivers to maximize their earnings in the marketplace. Complicated decisions in the old system included, for example, decisions such as whether or not to reposition to a different location, or whether or not to accept a ride at a given PT level. These were particularly hard because other drivers concurrently faced the same decisions, and everybody's earnings are affected by everybody else's decisions. Let me spend one slide on each of these to provide some illustrative examples on the sort of scenarios that drivers used to face. Let's first consider a driver's decision to reposition. The figure on the right-hand side displays the prime time markup multiplier in 3 different locations in the same city: blue, orange, and green. The x-axis is indexed by time, covering an interval of roughly 2 hours. On the y-axis, we see the markup, which is proportional to the driver fare. The higher the markup, the higher the fare. Now, if we consider a driver in the blue location at 7:30, she might wonder if she should reposition to the orange location, where earnings are higher. Looking at this figure and realizing that the driver observes only an instantaneous snapshot of the prices, it's not at all clear. Repositioning comes at a cost, and by the time she makes it to the orange location, earning opportunities may actually be better in the blue location than in the orange location. A similar decision arises for a driver in the blue location who receives a ride request from a passenger in the green location. Since the driver fare in the legacy system was based on the rider's prime time, drivers in one location may be offered trips with lower prime time markups stemming from a different location. In this example, the driver then needs to decide whether to accept the ride with the lower prime time markup from the green location, or to stay idle in the blue location and hope for another ride request with a greater prime time markup to arise. Finally, as I said before, these decisions are not made by individual drivers in a vacuum. If you consider this situation here, we have 4 drivers and no riders in the green location. In the orange location, we have 1 driver and 3 riders, and in the blue location, we have 4 riders and 2 drivers. In order to make sure that riders who request actually get served, the platform may set its price in the blue location so that half of the riders request, and in the orange location so that 1/3 of the riders request. At the same time, the platform may want half of the drivers in the green location to go to the blue location and the other half to go to the orange. In that case, all riders would eventually be able to be served, all drivers would get to serve a ride. We really get to a win-win-win scenario between the drivers, the riders, and the platform. But if the drivers observe only the PT markups, but neither the number of riders in each location, nor the actions of the other drivers, then there's really no way of setting prices in such a way that would guarantee or even incentivize this particular outcome. The result of this experience was somewhat dissatisfying for drivers. Here's a quote of a driver complaining on Reddit about primetime, the legacy system 3 years ago. It would show those areas always red. Red is what signifies primetime on the map. As soon as I got there, they're cold. I get a passenger, and as soon as I leave the area, it's hot again. We can imagine various ways to improve the driver experience. First, we could just try to set the rider prime time in a better way. But that does not really seem to address the issues that the drivers were facing. We could slow down how fast rider primetime updates. For example, have it update only every 10 minutes. That would maybe resolve the first issue with repositioning, but it would also severely restrict primetime's ability to respond in real time to market conditions. This is a strength of primetime that we would really not want to weaken. More importantly, it clearly wouldn't help drivers coordinate. So what we converged on instead is a decoupling of the driver and the rider primetime experience. The development of this new experience is what the rest of this talk is about. The new driver experience is called personalized power zones, and it works as follows. Drivers receive a location-bound incentive to reposition. The incentive is funded through the primetime paid by riders, and it's guaranteed to be paid out to the driver if the following two conditions are fulfilled. First, the driver needs to reposition to the location suggested by the incentive. And second, the next trip request that the driver receives needs to be accepted and completed. If those two are fulfilled, then the driver receives the incentive for the next trip. And this holds true even if the rider on that next trip did not actually pay prime time at all, or paid less prime time than what the incentive promised to the driver. Now, setting such incentives involves at least two major technical challenges. First, we need to decide which drivers to incentivize to reposition and where they should be repositioning to. Second, we need to decide how much to offer to each driver as an incentive for repositioning. Those two decisions are not independent, and they're actually quite tricky. For example, we want to spend the amount of prime time that riders collectively pay, but future prime time is hard to predict. And in particular, it is itself affected by the driver's repositioning actions, which in turn are affected by our incentives. Figuring out these two challenges was really a fundamental requirement for the new driver experience to be successful. Next, how you will describe how we did it.
Thank you, Daniel. We begin by describing what is assumed to be known initially. We know for each location the current number of idle drivers and expected demand through our forecasts. In addition, we know 1, whether we can reposition a driver from a specific location to another, and 2, the probability of the driver taking the desired positioning action in response to an incentive. These are machine learning models learned from available data that have been empirically validated. Lastly, we have for each location a current budget estimate. We'll describe this in greater detail later on. Based on this information, we need to decide on the set of drivers for whom we provide an incentive to relocate and the destination that we want them to relocate to. In doing so, we are constrained to not overspend the budget. Each driver that receives a PPZ incentive then makes a stochastic decision based on the driver's location and the location to reposition to on whether or not to reposition. Upon drivers relocating, the platform sets PT price markups based on the new driver locations and the forecasted demand. The prices are set using what we call a reserve level, which is a baseline minimal number of idle drivers that are available to be dispatched for any upcoming rider requests. This ensures that service levels remain high. The prices are set to, roughly speaking, serve as much demand as possible, without depleting the supply beyond this reserve. Upon seeing the upfront ride fare on the app, the rider chooses whether to convert and request a ride. Based upon the realized ride requests and the repositioned supply, the platform dispatches drivers to riders, maximizing what we call no PT bookings, the revenue of the ride request served without including the PT markup component. By not including the PT in the objective, we avoid edge case scenarios in which we may move drivers away from demand to increase the prices of the demand served, and thereby hurt longer-term retention of both riders and drivers serving them. Let's talk next about budgeting. This is fundamentally difficult because of the fast-paced dynamics in the system. In fact, when we first rolled out PPZ, we did not have a robust method in place that kept spending in check. This led to erratic system behavior, including vast overspending of our budget at times, and simply not spending at other times. In one early test, the system's erratic spending required the test to be abandoned completely and the changes to be rolled back in the entire city. In order to scale PPZs to Lyft's 320 cities, we require the robust and scalable approach to control spending that we now describe. The key insight we found was that fast location-specific real-time data based on upfront fares at ride dispatch can substitute for good prediction. So rather than trying to develop models that predict the PT arising from future ride requests, we limit ourselves to only those ride requests that have already been realized. Doing so requires really careful and accurate bookkeeping, as rides may often be canceled, adjusted, or swapped. All of these may change the PT amount the riders pay, and we keep track of current budget estimates based on all of these events. These budget estimates are location specific, meaning that we divide a market up into many small areas and have a local virtual account in each one to keep track of all the PT that has 1, come in through rides completed, 2, is expected to come in through rides requested or underway, and 3, is already spent on incentives given to drivers. These accounts allow us to restrict our incentives to locations where PT has been collected. The intuition for this is that the supply shortage is generally quite autocorrelated at each location, such that PT values now, while volatile, nevertheless indicates a need for more drivers. We call these location-based accounts escrow accounts, and together, they form the escrow mechanism that keeps track of the spendable PPZ budget. Let me illustrate pictorially how the escrow system works. As rider requests appear and get dispatched, as shown in the pink circles, the escrow system tracks the location of pickup and the promised portion of the PT in the overall ride fare. The system then looks up virtual escrow accounts associated with various locations near where the ride dispatches are occurring in the city. This is because these are the accounts that will be updated based on the ride events. Based on the proximity of the virtual escrow accounts to ride pickup locations, we add the incoming PT budget to escrow accounts local to the ride dispatches neighborhoods. There may, of course, exist other accounts that have already been filled up and have non-zero balances that can be used for future PPZ spend. Similar to the incoming PT budget, we subtract the PPZ bonuses that dispatch drivers have accumulated so far from escrow accounts that the PPZs are funded by. A single PPZ can be funded through the combination of balances in different escrow accounts. The allocation of funds from escrow accounts to PPZ offers is a side product of the PPZ optimization problem. In a nutshell, the joint optimization of budget and repositioning becomes a high-dimensional and intractable Markov decision process. We decompose the intractable problem into 2 separate problems, the repositioning problem on the left and the incentive computation problem on the right. The repositioning is still a difficult optimization problem due to its sheer size. In many markets, the number of locations can be up to tens of thousands, which means that the number of combinations of driver origins and destinations can be on the order of hundreds of millions. Solving problems of that magnitude within seconds as required of our real-time application is not feasible. However, using aggressive pruning strategies that provably preserve the optimal solution, we reduce the problem to a manageable size of roughly 100,000 variables and constraints. Now, we provide a description of our sequential algorithm resulting from the problem decomposition. As explained before, we update the escrow mechanism's account balances as events such as dispatch and completion occur. These account balances are the real-time budget we have available to spend at various locations in the city. Our driver positioning subproblem is to maximize the no PT bookings in the entire city. The key decision variable is a set of PPZ allocation fractions from some location with open drivers to another location with supply shortage. These allocation fractions tell us how many drivers in any one location we want to incentivize to move to another location in the decision period. Decisions to provide repositioning incentives are made based on 1, constraints on the service level, 2, the dynamics of how drivers respond and move vis-a-vis PPZ incentives, and 3, budgetary restrictions arising from the available escrow account balances. The service level constraint ensures that demand, subject to pricing, does not exceed supply at the location's supply spatial neighborhood, wherein drivers may be dispatched riders. That is, in each location's dispatch neighborhood, the market is balanced by simultaneously inducing PT and incentivizing drivers to move via PPZs. A notable aspect of the budgetary constraints is that while local account balances are aggregated and tagged to discrete locations, they are accessible to PPZ offers that guide drivers to any destination location within some spatial contribution radius around the escrow accounts location tag. Recapitulating the design of the escrow mechanism, the intuition is that a driver that reaches a specific PPZ destination can subsequently be dispatched not only to the destination location's riders, but also to riders nearby. Given the positioning incentive allocations from the driver positioning subroutine, the incentive computation subproblem attempts to match the dollar payout to the case where every driver sent to the same location is offered the same bonus and expectation. This is the so-called normalization procedure where we divide the escrow balances by the number of available drivers nearby. The rationale is as follows. The balances at each location represents the sum of the PT markups that each rider will pay for trips of different lengths. Since we cannot know which ride request is dispatched to a driver at some location ahead of time, a fair approach is to average the expected PT income over all possible trips that a driver can be dispatched to from that location. This results in an even split of the expected PT income amongst drivers. Finally, the system acts as based on the computed PPZ incentives for a fixed time interval until the algorithm is rerun for the next time period. This is typically on the order of a few minutes, such that the PPZ incentives are fresh with respect to the demand and supply distributions. Drivers who are already provided a PPZ offer and are moving towards their destinations do not get another PPZ offer, but are instead traced moving across the city. This is to prevent bad driving experience. Next, Davide will present results from numerical simulations and actual experiments that demonstrate realized business impact when PPZ is run in production in our 320 markets.
Thank you, Oi. Testing and productionization is a process that every new product at Lyft needs to go through. This allows us to maintain a high quality bar for our production systems and ensures that every new feature we add makes Lyft better. We give an overview of the process of productionizing the PPZ product. We start by introducing our testing strategy, which involves pre-launch numerical experiments as well as live experiments. We then discuss some key challenges in live testing PPZ in the presence of statistical interference and how we overcome these challenges. We conclude with a presentation of our results and the broader impact that this product had on Lyft marketplace. We carried out numerical simulations using historical data in backtests to iterate on our algorithm in a safe, non-production environment. The backtests enable us to understand computational needs in production, understand how the model handles specific scenarios, and get an initial performance estimate. We test two different objective functions, rider request conversion and no PT bookings. Using a behavioral model learned from historical data, we can compare market outcomes for the PPZ allocation to the legacy system benchmark. The relative gains are positive, as you can see from the chart on the right-hand side. And notice also that the distribution has a right skew. This is because we are sampling hours uniformly at random, and most hours of the day do not have any PT at all. However, it is important to highlight that the times that do have prime time are the busiest times, and they represent a sizable fraction of our business. That is why the overall impact is substantial, as we'll see from the live test results. As I mentioned before, when we are ready to roll out a new product, we have an initial phase of live user testing to evaluate the impact on the marketplace and on the users. Unfortunately, for PPZ, the most commonly used technique to get unbiased causal estimate of marketplace effects, which is switchback tests, could not be used. A switchback test requires randomizing and assigning treatment based on time. For example, test version A of a pricing model in hour 1, then switch back to version B in hour 2. In the PPZ versus legacy system test, the two treatments had a very different user interface, and switching back and forth between the two variants would have been a confusing and potentially also unsafe experience for drivers. We instead relied on a driver split test when we randomized treatment by user. This required a new causal machine learning framework to correct for the marketplace interference bias in our results. Results are as follows. Most importantly, we saw a statistically significant increase in our core metric, no PT bookings gain, a 0.5% increase, which translates into tens of millions of dollars of incremental revenue per year. Furthermore, we saw significant improvements in other key marketplace health metrics. These included reductions in driver arrival times, driver lapses, and especially driver cancel rates. The improvement in these metrics makes for a better platform experience for both drivers and riders. The PPZ product also had a broad direct impact on driver experience. Here is a feedback from a driver from Los Angeles that says, "It's a great incentive and makes me want to go to areas to earn more on my rides." In fact, we conducted surveys in a dozen cities and found that drivers show a greater preference for PPZ versus the legacy driver PT experience. PPZ also required a cross-functional collaboration. The product side focuses on building a usable tool that can unlock driver efficiency. The science and engineering side focused on building a high-performance decision system, and the operational side focused on quality of decisions. This is summarized well by Adriel Friedrich, our Director of Product Management, that says, "It's one of the many products we build at Lyft where algorithms, deep customer understanding, and operational rigor come together to deliver better outcomes for drivers and riders, but also significantly improve the company's financial performance." To conclude, we discuss how the legacy driver PT system had fundamental limitations that made for a worse driver experience and caused inefficiencies on the platform. We designed the PPZ product to overcome these limitations, but faced significant technical challenges in implementation and testing that we had to overcome with innovative solutions. Today, PPZ has fully replaced the driver PT experience, and much of its success is due to the applied analytics techniques we described in our presentation. Thank you for listening.